Hello class, welcome to Pre-Algebra Lesson 2.9, which is all about being able to understand scientific notation. By the end of this lesson, you should be able to use scientific notation to write very large or very small quantities. So let's just connect this name, scientific notation, with what we did yesterday. Yesterday we practiced taking really big numbers and writing them in this form where it was like to the power of 10, right? And we would always round our first number to be a nice whole number. Okay, so today we're going to do roughly that same thing, but today we're also going to have some decimals. So you're going to see me do things like 3.1 times 10 to the 8th, okay? You're also going to, on your assignments, be asked things like, is this written in scientific notation? So let's say I had 21.8 times 10 to the negative second. And you might be wondering, I think so. It's times 10 to the power of something. Why wouldn't that be scientific notation? Well, we have a couple of rules for scientific notation. In order to be, think of it almost like a grammar rule, okay? In order to be mathematically or mathematic grammar, essentially, correct, we need to make sure that this number is less than 10. Okay, so if we had a 21.8, we're not going to be able to use that as scientific notation. We would actually have to change it to be 2.18 times 10, and then I'll show you more later, but this would become a negative 1. Okay, and like I said, I'll explain why that changed later. But in order to be scientific notation, it has to be a number that's greater than or equal to 1, but less than 10. Okay, so greater than or equal to 1, but less than 10. So let's start with example 1, writing large numbers in scientific notation. Louisa is researching the approximate distance between the Earth and the Sun. Her father told her that the distance is 9.296 times 10 to the 7th miles. In an astronomy book, she found the image below. Which distance is correct? Okay, so we see that going from the Earth to the Sun, in her textbook, it says 92,960,000 miles. And her dad gave us a number in scientific notation. So which one's correct? Well, in order to figure that out, we could do two different things. First, we could try converting this number to scientific notation, or we could convert this number to standard form. So I'm going to show you both, okay? So I'm going to start by taking that 9, actually no, I'll start with the other one. Sorry, I changed my mind. But I'm going to start with this other one because it's similar to kind of what we did yesterday. So yesterday I would have made this like a 90 million, right? We would have rounded it and we'd say 9 times 10 to the, how many zeros are there? Well, there's 1, 2, 3, 4, 5, 6, 7. So yesterday, this would have been my answer. Today, it's slightly different. Instead of just saying 9, I'm going to put 9.296 times 10 to the 7th. Okay, so you do not change how you would write it other than you're just including that decimal. Okay, so you're including that decimal there. And now if I were to compare this scientific notation with the scientific notation her dad said, I would see this is written in the exact same form. It's the exact same number. So they are both correct. Both distances are the same. So both are correct. Okay, and I know I said I would show you like converting this one. We're going to save that for a later example. Okay, I want to mainly focus on drawing that connection to yesterday first. Okay, so for today, or for example 1, we would just say both of them are correct. Now what I want you to do is we have the height of Angel Falls, the tallest waterfall in the world, is 3,212 feet. How would you write this number in scientific notation? Okay, so think about what we did yesterday. Kind of take a look at how did I connect yesterday to today. And I want you to do that with this number, 3,212. Good luck. All right, for this problem, hopefully you realized that there were, if you were to round it, there would be 3 zeros. So you knew it would be times 10 to the third. And then you remembered you needed to include those other digits. And something that I don't think I've stated yet in this video, how do you know when you would include the real numbers versus the zeros? So if we look right here, you can see those 9296, those are the numbers I wrote down in my scientific notation, right? When you're doing scientific notation, basically you're eliminating anything that is a zero. Okay, so if there's a regular number that's not a zero, it gets included in your scientific notation. Alright, so that's why in this example, I wrote all of the digits. I said 3.212 times 10 to the third. And you might feel like, well, doesn't that defeat the purpose? Why wouldn't I just write 3,212? And I see your point. I totally understand. It's just a little bit easier for you to practice the skill with smaller numbers first, okay? So would I normally ask you to write such a small number in scientific notation? No, because it's just more work. But we're practicing with smaller numbers to make later steps easier, okay? All right, example 2, writing small numbers in scientific notation. So yesterday, again, we practiced writing those really small numbers, and we learned that we would write times 10 to the negative and then some sort of number, right? So here, I'm just going to rewrite this number to make it a little bit easier to count, okay? So yesterday, we would have just cut it off like right here, right? We would have just had this part. We would have said that this is 7 times 10 to the, and then I would say 1, 2, 3, 4. There were 5 zeros, so I would say negative fifth. Okay, so keeping that in mind, I'm still going to use that same exponent. So I'd have negative 5, because that's how many spaces that decimal point moves. But instead of just writing 7, I'm going to write 7.03. Okay, so I have 7.03 times 10 to the negative fifth. And that would be my answer. Now, if you're wondering to yourself, why did I include that zero? On the last slide, I said we're going to write down numbers that are not zeros. Again, you would be correct. However, there is a slight difference. When the zero is sandwiched or in between two non-zero numbers, you include it, okay? So when it's between two non-zero numbers, you are going to include that zero. But if there's just a bunch of zeros in front or like behind, like all of these, right? You don't write them. Okay, so I would have, for this really little number, I would have 7.03 times 10 to the negative fifth. Except not negative fifth. I am sorry. I made one big mistake, and I hope you can learn from this. That's why I'm not going to edit it out. I forgot to include the 7. That is the 6th digit. I would have to move that decimal place 6 times. So instead of being to the negative fifth, I actually need to change that to a negative 6. Okay, so now that I've probably thoroughly confused you, I'm going to just try to show one more time why it's a 6 instead of a 5. Alright, so the whole point of this scientific notation is that we're trying to move this decimal point to be after the 7. So if I were to count, I have to move it 1, 2, 3, 4, 5, 6 places in order to get it to be after that 7. Okay, so I'm sorry about that, but remember, I'm human too. All right, question 2. A common mechanical pencil lead measures about 0.005 meters in diameter. How can you express the measurement using scientific notation? Again, I recognize this is a pretty little number. Would I normally give you something this small? No, we're just doing it for practice to get used to the skill. Okay, go ahead and try this one on your own. Good luck. Alright, for this problem, hopefully you determined that it is 5 times 10 to the negative third. Alright, if not, please be sure to reach out for some help. I'm happy to help you. Let's practice converting scientific notation to standard form. Okay, so scientific notation, remember, is what we've been doing. It's when you take a number between 1 and 10 and you multiply by 10 to some sort of power, right? Standard form is just another name of writing numbers the way that you're used to seeing them. So like 3,212 would be an example of standard form, whereas the scientific notation of it would be that 3.212 times 10 to the third. Okay, so let's take a look. Kelly used a calculator to multiply large numbers. How can she write the number on her calculator screen in standard form? Now let's take a look at this. We have 3.5 E15. Have you ever seen an E pop up like that on a calculator? Maybe you have, maybe you haven't. That E is your calculator's shorthand or abbreviated way of saying we're talking about a scientific notation number. Okay, so what that's really saying is, so 3.5 E15, that's really saying 3.5 times 10 to the 15th. Sometimes you'll also see 3.5 3.5 E. Some calculators for some reason do 2 E's. More often you'll see 1, but it means the same exact thing, okay? Where you can just treat it like regular old scientific notation. So let's convert this to standard form. So I have 3.5, right? Well, I know in order to move that decimal to be after the 5, that's going to count as one space of moving it, right? So the way that I do this is I say 3 and then I start counting, okay? So I need to count to 15. So I would say 1, because the first place it moves is going to be that 5, but then every digit after that's going to be a 15, right? So let me just do this here. The pink is going to represent the count of how many times the decimal is moved. So 3.5 times 10 to the 15th, okay, 5 counts as the first movement, and then 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, and I can double check. So that was the first, second, third, fourth, fifth, sixth, seventh, eighth, 9th, 10th, 11th, 12th, 13th, 14th, 15th. So you can see that I have moved that decimal place 15 times. And just to make it a little bit easier on my brain, I'm going to go through and I'm going to add those commas to make it a little bit easier to see how this number is divided up. Okay, and also that's nice because it puts the numbers, the digits, in groups of 3, right? So 3, 6, 9, 12, 15. That's another quick way to count. Did I get all the digits? All right, so when you have a positive exponent, you are going to have a big number. When you have a negative exponent, you are going to have small number that is less than 0. Small number that is less than 0, meaning you're going to have a decimal. Okay, so let's try this one. We have 8e negative 9. So that's the same thing as saying 8 times 10 to the negative 9th. So when you have a negative number, I often start a little bit farther to the right on my page because I have to move my decimal to the left. So I'm going to move it 1 place, and then 2, 3, 4, 5, 6, 7, 8, 9. Alright, and I'm going to double check, did I move it the correct number of places? So I have 1 digit, 2, 3, 4, 5, 6, 7, 8, 9. So that light blue shows me that my count was right. I moved it 9 times, which is exactly what I wanted to do. So this number, this answer would be correct. The only thing I'm going to do is I like to put a 0 in front of the decimal just to help me see that decimal and know that it's not just a mistake on my piece of paper. Okay, so that is how you would convert that number to standard form. Now I'm going to have you try 2 numbers on your own. I want you to convert both of these to standard form. On Edpuzzle, it's going to prompt you with 2 separate questions. Okay, so you'll enter your answers on 2 different, or like in 2 different boxes. Okay, so go ahead and try these on your own. Good luck. All right, for that first problem, hopefully you got 9225, and then you had 15 different zeros following it. Okay, the way I do it though is I count my groups of 3. Right, here's 1, 2, 3, 4, 5 groups of zeros. So that makes it a little bit easier to read my answer. All right, and then for this second problem, hopefully you got 0.000000063. Okay, so 7 zeros and then 63. All right, if you have questions about that, please reach out for some help. I am happy to help you. Then our last page talks about just, the key concept, summarizing everything all at once. And I want to show you one last example on this page. Okay, so if we go back to that very first page that I showed you, I talked about 21.8 times 10 to the negative second and how that wouldn't be classified as scientific notation. And then I showed you that in order to make it scientific notation, I would actually have to make that 2.18 times 10 to the negative second. Okay, so why? Well, let's talk about what do each of those numbers equal. So 10 to the negative second means I'm going to move my decimal place 2 to the left, right? That means I would have 0.218. All right, and then if I were to look at this bottom one, oh, I have another, I'm just making all the mistakes. I told you that this would be to the negative 1. All right, so if I were to move that 1 place to the left, it would become 0.218. So notice, since I had already moved the decimal place to the left, I didn't have to move it 2 times anymore, right? I had already done one of those movements. So what you do is you add 1 for every decimal place that you have to move it to the left when you're writing it in scientific notation. So when I moved that decimal to the left, I really did -2 plus 1. So I moved this here, I added 1, and then once I did that, this was my answer, and this is now scientific notation. Okay, that last thing that I just showed you there on this page can be a little confusing and tricky. Please be sure to ask questions as you have them. I am more than happy to help you, okay? I hope you have a great day.